All right, so now we're in section 13.3, the fundamental theorem for line integrals. So, all right. You remember the fundamental theorem of calculus, right? You remember this theorem, right? How many recall that, this theorem from Calculus 1? Absolutely, Madeline remembers it. Well, the fundamental theorem of line integrals is similar, okay? Very similar. So basically this, the computing the area underneath the, underneath the curve from A to B, and fundamental theorem of line integrals, it really just depends on finding the antiderivative, evaluating it at the beginning point A, the end point B, and taking the difference. Let me show you the fundamental theorem of line integrals. This is the fundamental theorem of line integrals. We let C be a smooth curve given by a vector function where t goes from A to B, and we assume that f is a differentiable function of 2 or 3 variables whose gradient vector is continuous on the curve. Okay, so what this says is the line integral, okay, I want to say it the right way. The line integral of the vector field given by the gradient of the function f along your curve C can be evaluated simply by taking the difference of the function evaluated at the points RB and RA, which would mean B and A are times, right? Those are time values, right? So basically find out at, the starting time, what point does the particle start at, and then the ending time, what point does the particle end at, and then evaluate the function at those endpoints and take the difference, and you'll be computing this particular line integral. And the line integral, remember, that really represents, what that represents is the work that a vector field f given by the gradient of a function, that's the work that vector field does in moving a particle from point A to point B. But it's a very simple way, a very simple theorem to compute the work. But it only works where your vector function f is the gradient. So what I'm trying to say is this. Here's what I'm trying to say. So, okay, so here is your normal work. Okay, for a vector field f. What work does a vector field f do in moving a particle along a path, okay, along some path? That's this work. Now, how we compute that is what we use in section 13.2. We just did a problem where we computed work like this. But in the special case that the vector field f is equal to the gradient of some function, in that special case, okay, hold on. In that special case, the work and remember, the vector field f is equal to the gradient of some function. We call that function f, by the way, our potential function. that work is just equal to the value of the function at the endpoint, at the ending point, minus the value of the function at the beginning point. In other words, that by the F, we call this the FTLI, fundamental theorem of line integrals. The work can be computed by evaluating the function at the, I mean, you know, I want to say this right. The particle makes follows some path in space. We evaluate the function at where the particle ends minus the value of the function where the particle begins. It's that simple. And the proof, but it's only in the case where the vector field F can be written as the gradient of some potential function. That's the kicker, right? Not all vector fields, this isn't always true. You don't always, if the vector field F is equal to the gradient of some function, we call that vector field F a conservative vector field. But the thing is, not all vector fields are conservative. And so you can't always use the fundamental theorem of line integrals to compute your work. So the proof of the fundamental theorem of line integrals is not hard, but there is, I'll show you the proof, but let me just see here. Yeah, we talked about that, an initial point and a terminal point, yep. Here is the proof. Here's the proof. So let's take a look at this. This is the proof for the fundamental theorem of line integrals. Let's make that proof a little bigger here. Okay, so we start off with, of course, the definition of, you know, the dot product. I write out the dot product in the first step a little more clear, like I put in like a little more details. And then, wow, what's going on here? It looks like we're getting the chain rule involved. On that second step, the integral, we have the integral of, okay, it looks like the chain rule, right? So what's going on there? What's going on there? Well, let's see if we can make some sense of this. Okay, now give me just one moment. Hold on. One moment. Yeah. So I go to the whiteboard here, and I have a function that's evaluated at R of t, right? So this here, if I were to write out the function, on the first level, the function is a function of what? R of t is a position vector, right? It's a position vector. A position in three-dimensional space consists of coordinates, right? X, Y, and Z. Okay? I mean, R of t, right, is equal to, has components F of t, G of t, and H of t, right? That's your X, Y, and Z. But each X, Y, and Z are functions of t, right? X, Y, and Z are functions of t. So this is the chain. This is the chain. Okay. Well, hold on. I'm not quite there yet. Not quite there yet. So if I were to just move this down here. Well, all right, hold on. If I were to find the derivative of f with respect to t, okay, and that's the same as finding the derivative of f of r of t with respect to t. Okay, then by the chain rule, how many links are there going to be? How many links are there going to be in the chain? Based on the flow chart here, here's the flow chart. That's right, 3. Good, Ian. Good, Juliana. So here they are. Partial of f with respect to x times partial of x with respect to t, plus partial of f with respect to y times partial y with respect to t. And then finally, partial of f with respect to z times the partial derivative of z with respect to t. Right? So that's how we would find the derivative of this function. And of course, the function is a function of x, y, and z, but x, y, and z are functions of t. So are there any, and so you get this chain rule. Are there any questions on that? Maybe give me a thumbs up if you're good. Okay, Charles is good, and Gordon, and Ian, and Juliana, and Malik, and then some other folks. Good, good, good. Okay, well, let me go back then to the proof. Now, the proof should make total sense. So, what they do in the second step is the dot product of the gradient function and r prime of t would just be that what you see in the integral on the second step. But then we recognize that that chain rule is just equal to the derivative of the function evaluated at r of t. Oh, well, third step, to go from the third step to the fourth step, we're just applying the fundamental, we're applying the fundamental theorem of calculus, right? And that gets us to the last step. How many think that's pretty cool, that proof? How many think that's absolutely cool? Okay, Juliana's liking it. Yeah, it's always good to know why things are true. And what this means is then is that what this really means is you have what's called independence of path. Okay, you have independence of path when you compute the work. So you see, you're evaluating the work here, but when you evaluate the work, the fundamental theorem of line integrals says that the work's evaluated just by taking the difference of the function values at the initial point and terminal point of the path. It doesn't matter what the path does. It doesn't matter what the path does. Okay, so like for instance, if you had a conservative vector field, okay, and this were your point A, and this were your point B, okay, and this were path C1, and this here was path C2, the work would be the same if you had a conservative vector field. And that's a beautiful thing. Okay, so for instance, and also if you were to go along some closed path, if you had a conservative vector field and you wanted to find the work that the vector field does in moving a particle along some closed path, what would that equal? What would the work equal in that case if you had a conservative vector field? Well, if you're starting at R of A, so A is time A, and you end up at time B at the same point again, then the work is just going to equal 0, right? It's just going to equal 0 because the fundamental theorem of line integrals, you know, what does the fundamental theorem of line integrals say? It says, find the work by just taking the function about and at, you know, the difference of the function at the endpoints. Okay, you evaluate the function at both endpoints and subtract. But if the endpoints are the same as in a closed path, the work's 0. So like gravity, gravitational field is a conservative vector field. Okay, if for instance you were to let's say fly an airplane. Okay, how many have seen like an airplane do like a loop, or like a what do you call it? A roller coaster ride, do a loop, like one of those loops. Okay. I mean, okay. So here, let's say I'm going along this path. Gravitational field is acting on the path. Is the work positive or negative right now? I'm going this direction. Is gravity helping me or hurting me in moving along this path? It's hurting. So work is positive or negative? Work's negative. That's right. But now I start going down on my path. Is gravity helping me or hurting me? Going down. Is gravity helping me move? It's helping. So work is it positive or negative? Work's positive. Okay, so basically the balance between the negative work and the positive work that I just did in drawing this circle here, this curve, is 0 because I'm drawing it in a gravitational field. Okay? How many have heard of maybe independence of path in another class? I've heard of that kind of thing. Okay, Charles has. Excellent, excellent. Okay, so of course we like applying this fundamental theorem of line integrals. We like doing it, and it helps if we have criteria to establish if we have a conservative vector field. And one of the criteria is that if you have a vector field with components p and q, if the partial derivative of p with respect to y equals the partial derivative of q with respect to x, then you have you have a conservative vector field. Okay, that's one of the criteria. Let me just see here. And That would make sense, because let's say up here you start here with P and Q, and they're both components of the gradient. So a gradient field is always a conservative vector field, okay? So if you have a function whose, and its partial derivative is P, a partial derivative of f with respect to x is P, and partial derivative of f with respect to y is Q, okay? By Clairaut's theorem then, the partial derivative of P with respect to y would equal then the second partial derivative of f with respect to x then y. But by Clairaut's theorem, that equals the second partial derivative of f with respect to y then x, and that's just equal to the partial derivative of q with respect to x. So by establishing the partial derivative of p with respect to y equals the partial derivative of q with respect to x, means that q and p are both partial derivatives of f with respect to x and y respectively. And you know, in other words, your vector field is itself a gradient field. Okay, so I want to look at an example here. I want to look at one example. Okay. Okay, so take a moment to copy this down. All right, let me give you a few moments to copy this down. This example. Okay, so what we want to do is we want to find the work done by this force field in moving a particle along the curve C given by this position vector, where t goes from 0 to pi. Now, of course, we can always compute the work using what we learned in section 13.2. Okay? But if we could use the fundamental theorem of line integrals, it very likely will make our lives easier. Okay? Conservative vector fields are lovely, right? And they occur a lot in nature. So, and you're living in one, right? The gravitational field. So, in order to use the fundamental theorem of line integrals, we first have to establish if we have a conservative vector field. Okay, so on that note then, let me go to the next page. Everybody has this copied okay? Maybe give me a thumbs up if you're good. Okay, excellent. Okay, well, let's first see if our vector field is a conservative vector field. I'm going to use the theorem. Well, I showed you theorem 5, but it's really theorem 6. All I need to do is if the partial derivative of p with respect to y equals the partial derivative of q with respect to x, if they're both equal to 2, if they're equal to each other, then I have a conservative vector field. And it turns out in this case they are. Okay. So now that I have that, that's great. But in order to apply the fundamental theorem of line integrals, we need to find a function f of xy. Okay, this is a two-dimensional problem, this problem that we're doing. We need a function f of xy such that the gradient of the function equals the vector field. And this function of x and y is called our potential function. Okay, let me give you a moment to catch up here. Okay, so how are we going to find this potential function? Well, here's what we do. Here, let's remember what potential function means, right? Potential function means that the gradient of the function is equal to the vector field. The vector field has components p and q, right? P and q. So we're going to set p equal to the partial derivative of this function, whatever it is, with respect to x, and then we're going to set q equal to the partial derivative of f with respect to y. These are equations 1 and 2. And this is the procedure you need to use. This is what I'll be looking for on your exam as well, when you find a potential function. So, of course, we're interested in the function. We're not interested in the partial derivatives. We're interested in the function f of xy, right? So if I look at the first equation here, okay, this one here, how can I learn about my function f from its derivative, from its partial derivative? What would I have to do to get back to the function f? To get back to the function f, what procedure, what math operation would I need to do? That is right, Charles, that is right, Ellie. Take the integral. So what I'm going to do is I'm going to integrate this first function with respect to x. And I'm going to show that on the next page if we're good. May I go to the next page? Everybody has this copied okay? Give me a thumbs up if you're good. Thumb. All right. All right. Okay. Very good. Well, here we go. Okay. So, all right. There are the two equations, 1 and 2. I'm going to integrate the first equation with respect to x. So if I do that, then the partial derivative, the integral of the partial derivative becomes the function that I'm looking for. The antiderivative of 3 with respect to x is 3x. The antiderivative of 2xy with respect to x is x squared y. And then I have to allow for there to be a gy function, because the derivative of a function of y with respect to x is 0, right? So in other words, what I'm saying is if I were to take the partial derivative of this function with respect to x, I would get back my first equation here. So I need to have the gy there. I have to be as general as possible. This is what's called without loss of generality. Okay. Now we keep in mind that So now what I'm going to do is I've utilized the first equation up here, but I've not utilized the second equation. Well, the second equation is about a partial derivative of f with respect to y. So what I'm going to do is I'm going to take this equation here, and I'm going to, equation 3 I'm calling it now. I like to got to keep track of things. I'm going to differentiate number 3 with respect to y. And if I do that, I'm going to get the partial derivative of f with respect to y equals 0 plus x squared plus g prime y. So the partial derivative of f with respect to y is x squared plus g prime of y. Now what I'm going to do is I'm going to compare. I can compare the equation 2 here. I can compare equation 2 with equation 3, equation 4. And I can find out something about g prime of y, because you know, in my function here, my potential function f of xy, the only thing I don't know about is, hey, what's g of y equal to? Well, now I can equate equations 2 and 4 equal to each other to learn about what g of y is. Well, g prime of y would have to be negative 3y squared, and therefore gy would be negative y cubed plus some constant of integration k. And therefore, I have my desired potential function. There it is. Okay. Are there any questions so far? All right, well, we established that our vector field was conservative. Now we found our potential function. Now to compute the work done by our force field in moving a particle along that curve C, now we can apply the fundamental theorem of line integrals. Okay. So may I go to the next page? Let me know when you're ready. Okay, excellent. Okay. All right, Juliana's good. All right. Okay, So we're going to apply the fundamental theorem of line integrals. Here's the theorem. Now I might go over a few minutes here. If you can stay a few extra minutes, I'd be grateful. But it won't be. There's only one more page after this. So here's the fundamental theorem of line integrals, and here was that position vector. That defines my curve C, right? My curve C is defined by that position vector. As it moves, it traces out a curve C. As it moves with respect to time, it traces out a curve C in the XY plane. So the beginning time is 0. So R of 0 is equal to 1J. That's when the particle starts moving at time equals 0. And then the particle stops moving at time equals pi. So it'll end up at position negative E pi J. Okay, and so I apply my fundamental theorem of line integrals to get the result at the bottom of the page. All we have to do now is evaluate that. Okay, so are there any questions at all? Hyunu, are you feeling good with it? Okay, good. Noah, how about you? All right, well, Madeline, how about you? Are you all right? Good. How about you, Malik? Good, good, good. And Ian, you're doing all right? Good. Think I've, I've acknowledged everybody, right? All right, let me know when you're ready, and we'll go to the next page and finish this off, finish this problem off. Okay. Charles is good. Kino's good. Juliana's good. Excellent. Gordon. All right. Wonderful. Wonderful. Okay. All right. Well, here we go then. So now we evaluate it. Okay. So remember what our function was. Our function, our potential function. Here, let me write it at the top. I'll write it over here. I think this was a really nice class today. I really feel you learned a lot, and I like it that I like it that I could, show you why things are true. Okay, so the potential function, right, is f of x, y equals 3x plus x squared y minus y cubed plus k, right? So I put that there for a reference. So, here's 3x plus x squared y minus y cubed plus k. Okay, and and again, that's when x is 0 and y is negative e to the pi power. And then here we go again. Hold on. All right, this was 3x. Now we have 3x again, plus x squared y minus y cubed plus k. The k's cancel out, and when you're done, you're going to get an answer where the, you know, and this, again, this is your work. Your work is going to equal e to the 3 pi power plus 1. And that's an exact answer. WebAssign wants that. I want that. That's the best answer. This is much easier than computing this integral directly. Okay? All right? Much easier than computing the work directly using the definition of section in 13.2. We still need to know the definition in section 13.2 and be able to use it, because not every vector field is going to be a conservative vector field. But this one was, and we had, you know, and this was good. How many like the fundamental theorem of line integrals? How many is that of you like that? It's like yay. I think it's pretty cool. Okay, I agree, Charles. Definitely easier. Definitely easier. Are there any questions? Okay. Thank you, Malik. Okay, then I'll stop the recording.